So, today's topic is going to be something that you guys did and have been playing around with since you were little kids. Okay? Today's topic is magnetism. Okay? Now, back in the 1800s, a group of physicists realized that electricity and magnetism were linked to each other. And so ever since that day, since that unification of the electrical concepts and the magnetic concepts, okay, our society has marched forward. And it was that very connection that eventually would lead to the development of the modern electrical society that we have today. But we got to start with, what is a magnet? Okay? Now, everybody knows what a magnet is. If I ask you, you could tell me, give me an example of it, but what's actually going on in it? Okay? What is an actual magnet? Most people would just go, huh? It's the thing that metal things stick to. Okay, but what is it? Why does it do that? Because it does. Okay? We all played the game when we were a little kid where you took the refrigerator magnet, you put it under the table, you made the spoon dance, right? You made it move around, or you had those little toy cars that had the little magnetic connections at the end, and you push them around and stick them together. We all had those sorts of things when we were a kid. We didn't know how it actually worked. Well, magnetism, it's relatively simple. It comes down to the simplest basic building block of matter, which is the atom, okay? If we look at an atom, right? You've got your little proton in the nucleus, or protons, however many you may have. And you've got your electron. Now, aside from the obvious charge difference, okay, that electron moves, right? Electrons orbit around the nucleus. You guys spent the whole year learning all about this in chemistry. Well, as that electrical charge moves, okay, it generates a force. Force of attraction, force of repulsion, right? That force, that tiny little force, is a very tiny little magnetic force. It can pull things in that have an opposite charge, and it can push things away that have a negative charge. You guys all know this basic rule of magnetism. So every atom is like a tiny little magnet. Does that make sense? Okay? So then the question is, well, why isn't everything magnetic? Why can't I just go up to a piece of metal and stick to it? Why isn't everybody Magneto from the X-Men and flipping cars over and throwing things around? Because we're all made of atoms, and if our atoms are all these tiny little magnets, then why aren't we all magnetic? Well, because we have to look at the objects we're talking about. So let's say I just have a substance, any substance, doesn't make a difference what it is. That substance is going to be made of all these atoms. Okay, so I'll do the same color scheme that we have going here. Okay. So there is our atom. Now, we've got a little nucleus with a positive charge in the center. And we've got our electrons. And on this atom, the electron is here. On this one, it's here. On this one, it's over there. On this one, maybe it's here. On this one, it's up there. On this one, it's down there. This one's here. This one's over there. Okay? Now, all those electrons are moving. Are they ever all going to be facing the same direction at the same time? Are they? Are the fields from each one ever going to be lined up and lying on top of each other and strengthening each other? Yes or no? Do we think they're all going to be in the same point, pointing in the same direction as they spin around? Yes or no?
No.
Okay, so what ends up happening is, since none of them are lined up with each other, you're not going to get this thing being a magnet. So this object is going to be a non-magnet. Now I'm overly simplifying this out, but basically that's what happens. But in some objects, whether they be naturally occurring or man-made, so you could have something like magnetite, which is a mineral that you guys all learned about in earth science, which is a natural magnet. Okay, and then there's obviously magnets that we can create. But in a magnet, okay, you have the same basic structure, right? You got your object. Okay. It still has its electrons, it still has its little protons in the center. Like that. But the difference is the spin of the electrons as they move around, as they cycle around, is pretty much lined up. And so your electrons are all aligned with each other. And so the force that they generate, okay, is all aligned with each other. And so what you're going to do is you're going to generate this force across the entire object, and this object will now be considered to be an actual magnet. So the difference is the lining up of the electrons versus the non-lining up of the electrons. Once again, overly simplified. Okay? Cool? Now, what happens when these magnets occur, okay, is they're going to now have the ability to push or pull on charged objects. Okay? Now, the second that we use this word, these words, push or pull in physics, what are we talking about? A force. So there is a force that we generate, and we call this the magnetic force. Okay? This magnetic force is what causes these charged particles to get pushed. Okay? And so when we look at a magnet, it's going to create these lines of force. Right? And we talked about this before when we talked about gravity. We talked about this before when we talked about the electrostatic force, right? When you have an object that's generating lines of force, it's going to create an area of influence around the object, where anything that is affected by that force is going to be affected by that force. So for example, when you have an object with mass and it creates gravity, you create a gravitational field around that. And any object that has mass is going to get pulled in towards that center object, right? Best example, Earth. We said when you have the electrostatic force, okay, you have an object that generates the electrostatic force. Any charged object that comes within a certain distance of the object creating the electrostatic force is either going to get pulled in or pushed out, depending on if it has the same charge or the opposite charge. Magnetic force works exactly the same. Okay? The magnetic force is going to affect objects that have a charge. It's going to pull them or push them away. And so what you create is you create a magnet. Now, magnets, typically, you guys have seen them before, are going to look like this. And they're going to have two sides. They're going to have what we call a north pole, and they're going to have a south pole. All magnets have a north pole and a south pole. Okay? All magnets must be what we call a dipole. Okay? And you go, well, Mr. G, what happens if I just chop this in half? If I chop this in half, I would not get one side that was all north and one side that was all south. What I would get is two smaller magnets, one with the north pole and one with the south pole. Okay? You can never get what we call a magnetic monopole. They are theorized to have existed and would help with the whole, you know, what exactly happened to the Big Bang and string theory and all those things, but that's way above your ilk right now. So for now, we will just say we have dipoles. Does that make sense? Yes? Okay. So what's going on with these? So if we're looking at these, it's relatively simple. Okay? In a north pole, the force, okay, comes out. The lines of force come out. In a south pole, the lines of force go in. Okay? So the lines of magnetic force come out of the north pole and go into the south pole. Does that make sense? Yeah? Okay? Now, if you have a single magnet like this, what you're going to get is going to get a closed loop. You're going to get lines that look like that. Like that. Okay? Magnets always create these closed loops that look like this. Does that make sense? Yes? Okay? Now, these lines are just like any other line that we used to talk about, right? These are your field lines. Okay? But we don't call them field lines. What we call them is, we call these magnetic flux lines. Okay? All they basically show us is they show us the directionality of the magnetic field and the magnetic force that creates that magnetic field. Does that make sense? Yes? Cool? Okay. So, if you have a single magnet, your magnetic flux lines are going to look like this. They loop from one to the other, one side of the magnet to the other side of the magnet. Okay? If you take a magnet and you take little bits of iron, you sprinkle it on a paper that the magnet's on, you'll actually be able to see this. Okay? Now, the field's going to look different depending on what sides of the magnet you're using. If you use one magnet, you get that. But let's say you had two magnets. If you have two magnets, and you take the north side of the magnet, and you pair it up with the south side of the magnet, you're going to get flux lines that form a closed loop from one side to the other. Like that. So if you have opposite poles facing each other, you get this pattern. Simple, straightforward, easy to understand. Okay? But let's say you had two north sides facing each other. Okay? Well, if you had this, your field lines wouldn't connect. Why? Because you've got opposite sides, and they're both pushing that force out, yes? So the line would come out, out, and when they get to that middle point, they're going to curve up the way. Like that. Now, if you notice, what don't the lines do?
They don't touch.
They don't touch, and they especially don't cross. Magnetic flux lines will never touch, they will never cross. They get super, super close, but they can't occupy the same place at the same time. Okay? Now, if you have north-north, it's going to look like that. If you have south-south, you're going to get the same shape of lines, but something is going to be different. What's going to be different with a south-south as opposed to a north-north? The lines what? They'll be going in, okay? So in this case, the directionality would be different. Picture's going to look the same, but the directionality of the lines is different. Does that make sense? Now, there is a giant magnet that exists right here. Okay? What is the giant magnet that exists right here, where you are? I'll give you a hint. You are here. World's biggest magnet. Any guesses? Nope. World's biggest magnet. World's biggest magnet. Any guesses?
The solar system?
Smaller. Earth. Earth is a giant magnet. Earth has a giant magnet in it, primarily created by the most massive part of the Earth, where most of the Earth's mass is, which is the
Core.
core. Earth's core is made out of what substance? You did this in earth science. What element is the primary constituent of Earth's core? Starts with an I, ends in a run.
Iron.
Thank you, and nickel. Okay? Both of which make absolutely excellent magnets, particularly when you spin them around and slosh them around with a liquid core on the outside and a solid core on the inside. You're going to create a really, really strong magnet. Okay? And so Earth has this incredibly strong magnet. Okay? When we look at the Earth, okay, the Earth has this giant magnet running through it effectively. It looks like a giant bar magnet. Now this is obviously a virtual image. It's created by the core and all that stuff. But what happens is it creates this giant field around the Earth. Okay? So the Earth has this giant magnetic field around it. Okay? We call that giant magnetic field the magnetosphere. And it's super important And the reason it's super important is that there is something that exists in our solar system that's trying to kill us. It also helps us and creates life, and without it, life would be impossible, but at the same time, it's trying to kill us. What am I talking about?
The sun.
The sun. Okay? The sun shoots out a constant stream of highly energetic particles. We call it the solar wind. Every once in a while we get solar flares and all these other things. Well, if the Earth didn't have this magnetic field, all of that stuff would hit the Earth, irradiate it, and make life utterly impossible. But since we have a magnetic field, that's a force, and since those particles coming out of the sun have a charge, this force can actually deflect those particles away from the bulk of the Earth and keep us nice and safe and healthy. So if we didn't have this magnet protecting the planet, our planet would look a heck of a lot like planets that don't have magnetic fields like Mercury and Mars. You'd have no atmosphere and there'd be all sorts of problems. Okay? Now, when we look at the Earth and we talk about it having a magnetic field and having a big magnet inside of it, okay? Well, we're used to talking about this part of the Earth where Santa Claus lives. What do we call it? The North Pole. And we're used to talking about this part down here where Happy Feet and all his penguin friends live as the South Pole. You all remember Happy Feet, right? From when you were kids, dancing penguin. Okay? And you go, cool, so that's the Earth's magnetic field. Except we have a problem. When you want to use the Earth's magnetic field, which you can to get around, you use a little tool called a what? What tool do we use that uses Earth's magnetic field? Sailors used to use it back in the days to tell where they were going.
A compass.
A compass, yes? Compasses point north, yes? Yes? Which means that that little needle inside the compass is getting pulled towards the North Pole, right? Towards the North Pole up here. But it's getting pulled. So if it's getting pulled, it means which way is the line going? Is it coming out of here or is it going into here? If that little metal compass needle is getting pulled in, which way is the arrow directed? Into the North Pole or out of the North Pole?
Into.
Into. Okay? That means the magnetic lines are going like this. Right? Well, wait a second. What did we say about the poles? We said which pole on a magnet pulls in? Say it loud, Samantha. The South Pole. So this pole, which we call the North Pole, we have to be more specific. The North Pole is what we call the North or the geographic North Pole, meaning that that's the northernmost point on a map. The South Pole would be the geographic South Pole, the southernmost point on the globe, yes? But when we talk about the magnet that's inside the Earth, the magnet inside the Earth is actually flipped. Up here would be the South Pole, and down here would be the North Pole. So this is what we call magnetic north, and this is what we call magnetic south. Does that make sense? So geographic north is actually magnetic south, and geographic south is actually magnetic north. Cool? Does that make sense? Now, this isn't a permanent situation. The poles reverse every couple 100,000 years or so. You guys learned about this in earth science when you learned about the rocks coming out of like the cracks in the ocean floor, and when the iron hardens, it points towards where the North Pole is and stuff like that. So we know this. Okay? Does that make sense? Yes? Now, what the heck does this all have to do? Other than the fact that refrigerator magnets are really cool, and your parents probably have way too many of them on their refrigerator. Okay? What the hell difference does magnetism make for you? Well, magnetism is incredibly important. The reason why is, like I said at the beginning of the lesson, it ends up being the basis for our entire electronic society. How? Well, once scientists started figuring stuff out about magnets in the early 1800s, mid 1800s, and the late 1800s, there were tons of scientists playing around with magnets, trying to see what they could do with them. Okay? Now, scientists realized that anytime you had an electrical object, you generated a magnetic field. Basically what we said, the electron has a charge, it's moving, you're going to generate an electric field, right? The basic rule is that if you have a charged object and it moves, it creates a magnet, or a magnetic field, I should say. Okay? Magnetic force and magnetic field. So scientists said, so maybe we can do it the other way. What if we can take a magnetic field and create a charge? Okay? Create a current. We can do that, we can create unlimited current, and we can make things run electrically. And that's exactly what they did. Okay? What they realized is that if you have a magnetic field, like this, okay? And I take a conductor. Say I take a metal rod, right? And I move that metal rod. So imagine the metal rod is here, the lines are going like this. If I move that metal rod through the lines, so I move it out and in, right? So I cut across the lines. Well, what they discovered is that if I take that metal rod and I move it across those lines, the force, that magnetic force, is going to make the charged electrons move. It's going to give them electrical potential energy. What do we call electrical potential energy? It's a fancy way of saying what? Voltage. So if I move this bar in and out of the field, I'm going to create a voltage difference. Some of the electrons are going to have one voltage, some of the electrons will have another one, so I'm going to create a voltage difference. Now, the second I create a voltage difference, I've done something. If I was to take that conductor and connect it to a wire, and let's just say we connected that wire to, oh, I don't know, a light bulb, and I went under the wire, thing like that, and I connected that wire, right? Well, when I'm moving this guy in and out and in and out, I create a potential difference. Well, the second I create a potential difference, the electrons are going to want to slide down that incline from the high potential difference to the low. What do we call it when electrons or when charged particles start to move? The movement of charged particles over a period of time. What do we call that?
Current.
Current. So I'm going to generate a current along this wire. And that current is going to move along this wire, and when it hits this object that provides some sort of resistance, in this case a light bulb, what is that light bulb going to do with that current? What would it do? You put current through a light bulb, what does the light bulb do? Turns on! Hey, light. Then that current's going to keep going all the way through and create this closed path of moving electrons with a potential difference. What did I just create? A what? A circuit. I created a current, and by closing the path on either side, I created a closed loop for that current to flow, which is what we call a current. I created a current where there was none. I induced a current. Now, what scientists realized is the second they stopped moving that conductor, the current went away. Okay? So in order to induce a current, I had to move the conductor through the field. And I had to move the conductor through the field in a very specific way. I had to make sure that I was cutting across the field lines. If I was going like this, and I was moving the conductor this way, would I be cutting across the field lines? Would I? No. Okay? If I went like this, I can cut across them. The best way would be to go like this. If I go like this. So I have to move perpendicular to the field lines in order to induce that current. So if my conductor moves perpendicular to the field lines, I can induce a current. Does that make sense? This right here eventually becomes the basis for all the electronics that we have. Okay? We call this electromagnetic induction. Electromagnetic induction. Okay? Does that make sense to everybody? Are we cool with that?
Yeah.
Okay, so that is the last